Good morning, everyone. My name is Cosimo Corsi, and I'm from the Technical University of Berlin. The work that I will present today has been carried out also in collaboration with the University of Applied Science in Berlin. And we developed a novel technique for the measurement of wall pressure fluctuations in shockwave boundary layer interactions. And this new technique is based on piezoelectric thin foils. First of all, I will introduce the flow case that we analyzed in our supersonic wind tunnel. Here on the left, you can see a Schlieren visualization taken at 20,000 FPS of our SBLI. And the flow is coming, of course, from the left to the right, and it's a Mach 2 flow. And you can clearly see the impinging shockwave in red. And this shockwave is generated the adverse pressure gradient that is creating the separation in the boundary layer, and it creates this classical lambda formation. And here on the right, you can better see the separation in this whole flow visualization. And in our test, in our wind tunnel, we have like a 50 millimeters of separation length. And as you can tell, this phenomenon, as you probably know, this phenomenon is quite unsteady. And usually with experimental investigation, we tend to look at this unsteadiness by investigating different means. And for example, like has been shown also by Alessandro before me, a good way of investigating this unsteadiness is to look at the wall pressure fluctuations. And this is usually one of the classical plot that we see is like a wall pressure fluctuation map of the pre-multiplied power spectral densities. This is from a DNS simulation by Bernardini et al. From La Sapienza. And as you can see, these the wall pressure and fluctuations are characterized by different, really a wide frequency range. We go from Struel 0.02 to 0.04 for the low frequency unsteadiness that is created by the shock foot. And then we go to the higher Struel number from the incoming boundary layer and then the separation region and the attachment region. And experimentally, this kind of investigations are done with different methods. The state-of-the-art methods are pressure transducers, for example, but they have a high performance, so they usually have a high frequency range, but they lack in space resolution. So we can build arrays of pressure transducers, but this is really costly. And another way is to use like a pressure sensitive paints, and this is the best solution for the space resolution, but they lack in the frequency range. And with our sensor, we want to fall in between these two techniques. So we want to create something that is easily applicable to complex geometries like pressure sensitive paints, but it also has good performances like pressure transducer, and also being cost effective. So in my talk, I will first talk about the working principle of our sensor. Then I will introduce it and show how it has been made and how we characterize it. And after that, I will introduce the experimental setup and show you some results in our turbulent shockwave boundary layer interaction test case. The working principle is quite straightforward. We have a polymer, special polymer layer that is called polyvinyl DN fluoride. And this polymer is piezoelectric, which means that if we apply a force over this layer, some charge displacement is generated inside the polymer, and charges are collected on the faces of the polymer. And so if we coat the faces of the polymer with metal, we can then extract those charges. And by means of a signal conditioning system, in this case a charge amplifier, it's possible to convert this charge into a voltage that is readable by a digital acquisition system. And one of the main advantages of this technique is that we can create a pattern on the metal. And so we can create a custom arrays of different sizes and from just a single foil, because the active area of the sensor is actually the overlapping area between the two faces. So we can go with, for example, in our work, we have used this technique. So a single, I mean, actually we've used a double side etching, but with overlapping areas, not these cross overlapping areas. They need a more complex electrical circuits to be, but it's possible. And this is a schematic representation of the sensor we came up with. And it's based on a flexible polyethylene substrate. And we screen print silver ink over it to create these wires that extract the signal from the active elements, and they bring the signal to the charge amplifier. And over that, we placed an insulation layer. We are screen printing an insulation layer to reduce the noise from the wires. And then we have a special print a special conductive layer that is conductive only in the thickness direction, so it's anisotropically conductive. And over that we have our piezoelectric active polymer, and with the silver ink on both sides to act as active elements. And if we squeeze all of these together, this is the final sensor, and it's composed. The one that I'm showing you in these slides is made up with a 6x3 active elements matrix. So it's 18 sensors in total, and the diameter of the sensor is 3 millimeter. And this is the connector that is then connected to all the acquisition system. And this has been implemented in a wind tunnel with a 3D printed plug. So we have something like that for the final instrumentation of the wind tunnel. And before moving to the experimental setup, so before showing you the wind tunnel, I will quickly go through some characterization we have done. And for that, we've used like a Kunst tube, which is actually it's just pipe pretty much with a pressure fluctuation source. In this case, we use a loudspeaker, and we can tune the length of the tube to a specific resonance frequency. So we can have a plane wave on the end of the tube, and we put our sensor and the reference sensor at the end of the tube, and we get a constant pressure fluctuations. And by doing that, we achieve this calibration matrix for our sensors, and this is just one position. And you can tell the response is quite linear. Yeah, here some sensors are broken, and these two are missing because of some lacks in because of the acquisition system we have used is only 16 channels. So we've removed a couple of sensors. And but one of the main drawbacks of this system is that it's also depends on temperature. As you can tell here, I've used the same setup. We put the Kunst tube into a heating chamber, which is not the best way to calibrate it, and that's why we need to do a proper calibration for temperature. Because if you change the temperature, the speed of sound changes, and also the resonance frequency changes, so the pressure is not exactly the same, even if we try to compensate for that. And but yeah, then that's why we are developing also still not ready compensation system for the sensor to have the correct values of the pressure fluctuations. And to conclude the characterization, we perform also like a frequency response test, and we've used a dropping ball impact test to get the frequency response. And here in red, you can see the theoretical values of the impact test. This is calculated based on Earth's theory. And in black, you can see the actual measurements from the sensor. You can tell it's matching quite well. So we can assume that our sensor is linear, as a linear flat response, at least up to 20 kilohertz here, but probably it's should be higher. It's just this is a limitation of this system, that it can only reach these values because of the material of the plug of the ball, the size of the ball, the mass of the ball. This cutoff frequency move. And this is our supersonic wind tunnel. It's like it's an open loop continuous wind tunnel. It has in-draft operation, so the air is sucked in by the outside. So the total conditions are ambient conditions. The air enters a silica gel drying chamber where the humidity is removed, and then enters the settling chamber where the turbulence is lowered, and it finally enters the test sections. And the test section are interchangeable, so we can change Mach number, so we can change the flow configurations. And I will show you now the test section we have used, and is composed by a Mach 2 Laval nozzle and a 10-degree shock generator that is creating the impinging shock wave that interacts with the boundary layer and creates our SBLI structure. And below of this SBLI structure, we placed our plug that I've shown you before with the sensor. And the sensor is located in a way that I will show you better the position of the sensor compared to the SBLI now. The first two positions here in red and green are located in the proximity of the separation shock foot. So we expect the low frequency unsteadiness to be captured by one of these two sensors. And this depends also on the total condition that we have. So if we measure in summer or in winter, this position changes a bit. So, and while all the other positions are under the separation bubble, and we expect higher frequency peak here. Yeah, this is the results. The time series we obtain from the sensor, the PSD we obtained. We have acquired all the sensors simultaneously. I mean, 16 sensors simultaneously at 200 kilohertz. And for 1 second acquisition time, we cannot get much from the normal PSD. We move to the pre-multiplied one. Yes. And as you can tell, we measure in the first position the low frequency unsteadiness with a Struel number around 0.04, 0.05. And then as soon as we move down under the separation bubble, we switch to Struel closer to 1. And if we compare them with the Q-light taken in the same Q-light measurements taken in the same flow, the Q-lights are state-of-the-art pressure transducers used for pressure fluctuations measurements. We can see that they are matching quite well. I mean, we cannot yet use it for actual pressure values because of the temperature issues that we are trying to solve. So these are just voltages and normalized voltages. Yes, but I think for already the dynamic behavior of the sensor is matching quite well with the Q-light. And so to conclude this talk, we developed a flexible PVDF-based sensor. We have calibrated in dynamically with a Kunst tube, but we need to implement a temperature compensation systems that we are already doing. And we have successfully detected different flow regions of the turbulent SBLI, and we validate the dynamic response against the Q-light. And the next step, as I said, we will try to solve the temperature problem, and we'll also implement the sensor in more complex geometries, because this is one of the main advantages of these sensors, that we can, for example, apply it on curved surface like compressor blades or overshock control bumps. So that's probably what we will do in the next future. So thank you very much.